Welcome to Growing World, the podcast where we explore the science of exoplanet through conversation with early career researchers on the front line of discovery. I'm Lorenzo.
And I'm Jeni. In each episode, we meet a guest who takes us behind the science of planets, stars, and the search for life in the universe.
Today, we are looking through a different kind of window, one shaped by mirrors, instruments, and the atmosphere of our own planet. Because even from the ground, we can catch the faint fingerprints of alien worlds hidden in starlight.
And to guide us through how astronomers are using high-resolution spectroscopy from Earth to reveal the composition and motion of exoplanet atmospheres, we're joined by Dr Mattia D'Arpa from INAF. Mattia, welcome to Growing Worlds.
Thank you so much for inviting me. It's a pleasure being here.
Mattia is a postdoctoral researcher at the Instituto Nazionale di Astrofisica in Palermo, where he studies exoplanetary atmospheres using high-resolution spectroscopy, which is one of the most powerful tools that we have for detecting the molecules and the wind that shape alien skies. He earned his PhD by characterizing hot Jupiter and ultra-hot Jupiters, focusing on how the spectra can reveal dynamical processes such as atmospheric escape and high-speed winds. At INAF, Mattia is part of several international collaborations using cutting-edge instruments such as harps, Jano, and espresso, which unfortunately is not the Italian coffee, and he combines their data with space missions like Ariel. His work helps bridge the gap between the precision of space-based telescope and the spectral resolution achievable only from the ground.
So, Mattia, I think it would be great to begin with your story. So, what first drew you into astronomy, and then how did you end up at spectroscopy? Is it all about the technology that drew you, the physics, or just the idea that we can read the atmosphere of another planet from light that's streamed across our galaxy? So, where does it all begin?
So I've always been curious about science in general. And then at some point I realized that I was really curious about astronomy, astrophysics and physics and trying to explain why things happens all around us, stuff like that. And during my third year of high school, I started doing some physics experiment during a lab at the high school. I was like, okay, this is the things that I have to do in my life is physics instead of, like, for example, becoming a doctor, a real one.
Mm.
I became a
Hey,
doctor
hey, hang
eventually.
on.
Wait a
We are
minute.
all real doctors here. We will not have that talk.
But the ones that you can call when you have an
Yeah.
emergency, like it's a life or death situation, you won't like calling me, probably.
Yeah, I mean, all we can do is soothe people with tales of the stars as
Yeah,
they die.
exactly.
Like that's where our use comes in. We can't save their life, but we can keep them calm.
I understand, but just don't ask me to save any life, and it's fine.
No. Yeah.
I decided to become a scientist, and I started studying in Palermo physics for the bachelor degree. And then I moved to Milan because I wanted to become an astrophysicist, and I wanted to do a new experience in my life. So I moved to Milan and I started studying cosmology, which was really nice. But I kind of felt that it wasn't the things that I want to do later. And so I went back in Palermo, which is my hometown, studying again exoplanets because my bachelor thesis was on exoplanets, and starting this time with atmospheres. And I think that I really liked back in the days and still nowadays the fact to try to assess what is and what is not in the atmosphere of an exoplanet, like what are the molecules or the atomic species. It combines several aspects of being a researcher that I like, for example, analyzing data, but also planning observations, trying
Mm.
to understand which target you want to observe and why, and also observe directly several facilities. So this was the reason why I started studying exoplanetary atmospheres. The high resolution spectroscopy actually happened because in Palermo, within an Italian collaboration, that is CAPS, we have the possibility to work with the Telescopio Nazionale Galileo in La Palma with the Alps North that we know the Alps instrument, and then of course also to work with Espresso along with other low resolution instruments such like aerial mission that will be launched. So I started with high resolution side, and I'm trying to move a little bit to the low one, but the high resolution at this point is deeply in my heart. So
Yeah.
I
So really, it's all about the travel, right? Going to La Palma and going, to all these different places.
you won't
That's
you won't say travel when you have to move from Palermo to anywhere else in Europe. It's always like 2 or 3 flights to go anywhere. Consider that when I go to La Palma to observe, it's like 15 hours of traveling and then spending a night at the sea level, and then the next day going up and observing, and then everything back once you have to everything again once you have to come back, but often without sleeping the nights.
yeah.
Really not about the travel. Maybe about the landscapes, but not the
Yeah.
travel.
Mattia, about the high resolution that just happened in your life, can you walk us through what it is, how it works, and what can tell us about exoplanets?
So, spectroscopy is the study of the light coming from a source, dividing it according to its wavelength, its energy, everything you want to call it. So you split the light like the water vapor do when the rainbow happens. And so the same things apply to the study of stars. So you observe a star, you have some cool instrument, like for example a spectrograph that split the light and allows you to see what happens, what really happens in the star. Let's say in the star, which is the thing that we observe. So you can see that if you observe a star, there are some markers in its spectrum, which are due to the elements, the atomic species, and the molecular ones that are in its atmosphere, which we call photosphere. And you can do the same with an exoplanet. It's just slightly different because what happens is that when the planet transits in front of its host star, part of the starlight is scattered, so the photons interacts with the species that are in the atmospheres of the planets, allowing us to see that in the spectrum some part of the spectrum is missing or has what we call an absorption feature. So you see that part of the stellar light has been absorbed by something, and this something is something that is in the atmosphere of the planet. So, like in my case, mostly atomic species because I work in the visible band with Earth's node. And so you can say, okay, now we are missing something here. It should be. We know from Earth lab that there should be a line of, let's say, iron here. So maybe in the planet we have some iron, and we of course started to do this with the star. That's the same thing that you do for the star. You can do it for the planet as well, but you need the stellar light because the
Mm.
planet does not have its own light. It's too faint. So we use the star. We wait for the planet to pass in front of the stars, and the atmosphere filters its radiation, and we study it. At least this is the transmission spectroscopy. To be clear, that is what I usually do.
So you do a lot with high resolution spectroscopy. So I guess that means that's lots and lots of detail in the spectra, lots of fine wavelengths.
Exactly. So the resolution depends on the ability of your instrument to split the light into narrow or wider channels, let's say. You can have something more detailed, like you were saying, with high resolution spectroscopy, where you are able to see and distinguish individual lines, like for example the ones that we can say this is iron. While of course if you go to lower resolutions, the line starts to blend all together, and you are no more able to distinguish all of them, at least all of them. Maybe the biggest one, yes, but not all of them altogether. And you start telling about bands more than lines. And of course, if you are able to study an individual line and you have more details, you can understand more about what you are investigating. The thing that you can acknowledge from studying low resolution spectra, for example.
So why bother doing the low resolution broadband if like all of the information is in the high resolution? Like why bother?
Generally, say nowadays, low resolution and high resolution kind of refer to ground based instrumentations and space missions. Because usually nowadays, bigger telescopes like the ones that we have, like the Telescopio Nazionale Galileo with Alps North, or the ones in Chile with Espresso and Alps, giant telescopes collecting a lot of lights with very stable foundations where you can put an high resolution spectrograph, while low resolution is performed by space mission, like for example HST, JWST, but also aerial. So it's more something like an engineering problems. To build an high resolution facility orbiting is not that easy. It seems we can't have high resolution spectroscopy from space.
So then I guess in space you can maybe survey more with the low resolution, so then you know what to target with the high resolution. Is that the
Well,
idea?
I mean, the two techniques are kind of complementary because low resolution also allow you to do different things. For example, you can focus on a wider range of wavelength, and you can have what we call a continuum, so you can see the true level of the stellar flux that you receive. While on high resolution, usually you focus on a narrower region, and you are not able to know what is happening globally and in the continuum. Most important, if you are on space, you do not have the Earth atmosphere, which
Mm.
can be a problem because the Earth atmosphere has the stellar one and the planetary one as well, do absorb light. And so what happens is that you also have to account for your own atmospheres while you are studying the other ones, and it can be challenging. I think that when I started my PhD, this was a, a problem that it seems to be like really bad. But then, especially at high resolution, I have to say that nowadays, focusing on individual lines, we are getting better avoiding the Earth atmospheres. But of course, we are still missing something. And of course, you have a lot of other pros observing from space. You know, you do not have to wait for night, for example, to observe something
Mhm.
like that. So yeah.
I also guess you may have some other complication from observing from Earth, right? Because true, you have your own atmospheres, but there are also other challenges like telluric absorption, the weather which is changing, the gravity. How do you handle this in high resolution spectroscopy from the ground?
So yes, of course, there are some major problems related to planning the observation, and then hoping, of course, that that night the weather will be nice and you will not have to put everything into the bin because some cloud decided that there was its moment to shine. Let's say.
Yeah.
Let's start from planning the observation. If you plan the
Mhm.
observation, you can try to mitigate these effects. Try to repeat to schedule more observations of the same target to acquire to be sure that at least once the weather will be nice, and you can try to model better the atmosphere above the place where you are observing. And we are kind of nice doing this. We are getting good. Of course, when you analyze the data, you work with what you have at some point. So you can correct for the atmospheric absorptions, like the telluric lines. There are a lot of tools that do that. And that's not a problem. If there is a cloud of or anything else, some failure in the instrumentation, which it can happen that sometimes the things that do not work, or the automatic pipelines fail and you have to reduce again all your data. It's just uh, trying to see where the problem is, and trying to get better fixing it. No tricks regarding this. Model your own atmospheres before studying the other ones. That's the first thing you have to learn. And I think that one thing that we usually discuss with my colleagues is try to not overestimate and overanalyze your data. You have
Mhm.
what you have. Try to get what you can get from your data without
Yeah.
trying to squeeze them. I don't know if you say this in English.
Yeah.
Yeah, it
Yeah,
was the
yeah.
Murphy law, right? If you torture the data long enough, they will confess anything.
Yeah.
Yeah.
Yeah. Yeah. How do you model the atmosphere when the atmosphere is continually changing, right? It's not even on a night by night basis, but every few minutes it's different to the minutes before.
Yes, of course, you to have to be time dependent in this case. But the thing is that when you start an astronomical observation, you record all the parameters regarding what is happening in that moment. So you know the air mass, so how much of atmosphere do you have above you, and you collect the humidity and all of these other important parameters to model your atmosphere. And since you know them point by point, let's say spectrum by spectrum, you can say, I have a tool that do model the Earth atmosphere, and I can model the atmosphere in these conditions, and I can do it for all the conditions that I have in a night.
So are like machine learning technologies and like AI, yes, AI is always an interesting phrase to bring up because some people hate it and some people love it. But are they changing the landscape? Are they helping with modeling the atmosphere, reducing the data, not, overworking the data, things like that?
Regarding the modeling the Earth atmosphere, saw something recently with machine learning, but I think that the tools we have, the analytical tools that we have at this moment, works really good. For the exoplanet atmospheres, yes, there is a lot of work that people are doing for use machine learning. I'm not pretty sure about artificial intelligence, but for sure, machine learning, there is a lot of people working on that. So my experience about employing machine learning to fit spectra is that I'm not really sure that is able to do it right now. It needs a little bit more of training. Will it be the future? Who knows? I'm not so they did not convince me a lot till now.
Mm.
But I'm really, really, really happy to learn and to see if machine learning can do the work.
What you can't see, dear listener, is that Lorenzo is giving Mattia the eyes, like
Yeah.
the evil eye.
But let's be honest, I have to say, Lorenzo taught me to analyze some data. And then we analyzed the same data with machine learning and it wasn't working. So
I have a lot to say about that, about this topic, but instead, what about the location where we put all these huge telescopes? Because building telescope that big that can work with high resolution spectroscopy, it's a huge effort. It's not only about money, and they cost a lot of money. It's also about people and time and hopes for the result. So you really need to put your telescope in a place where you can, well, but the weight is not changing that much, maybe, right?
So let me start from what I heard in the seminary that we have in at our astronomical observatory. The astronomical observatory of Palermo is one of I think it's the only one in Italy, along with Milan one, that is built in the city center. And of course, you understand that at some point where they started with the lights in the city and stuff like that, the astronomical observatory is not good enough to is not can stay in the city center. We need to move outside. And for the big facilities is the same. So we build these facilities in place without illuminations and also with stable weather conditions. Like for example, Chile, where we have in English is Andes, right? I'm sorry, I realize that I do not know how to say Andes in
Andes.
Andes. Yes, I'm sorry.
Like, so we have this joke in English, which is like, where are the Andes? And like people say Chile, but it's like you go, no, they're at the end of my armies. Like arms.
Oh,
Oh, it's good.
Yeah.
oh.
And so, Andes are not only for bad English humor jokes, but they are good for a good place for building instruments for some sort of geographical conditions. They have stable weather, low levels of humidity, and of course, there is also the altitude of the Andes is helping us, and that's the reason why the other instrumentations have been built on facilities that are high in altitude, like for example the Canary Islands or some other facilities all around. You understand that Palermo's observatory on sea level in the city in the city center is not good
No.
for nowadays science.
Yeah, I can imagine how it might be a problem, just even you think about living in a town and city and you're just trying to use a pair of binoculars or a small telescope, let alone trying to
No, you won't see
detect the
anything.
light from an atmosphere of an exoplanet that's hundreds of light years away.
No, we collect some transits. We are able to detect some planet transiting. So you can see that, for example, if you observe the star and the planets pass in front of the star, there is a decrease of the flux that you are collecting because a part of the stellar disk is obscured by the planet. And we can do this from here, but of course we can't obtain the high resolution data that we are able to
Mm,
obtain in huge facilities with a lot with less light contamination and way better condition from humidity, temperature, and stuff like that, of course.
yeah. Yeah.
About the instruments that you use, harps, espresso, and gaps, where are they located?
So ARPS North and Giano B are two instruments that are in the Telescopio Nazionale Galileo that is located in La Palma, Canary Islands. So the telescope is Italian, but has been built
Mhm.
in La Palma because,
We know where to go for good weather and vacations.
yeah,
Right, you
kinda.
say this. You say this. I went on a cruise in March, and it was, like, to those islands, and they get about 5 days of rain a year, right? And
Were
for
those
my
5
cruise
days?
we're all on my cruise. Like,
No,
every
no!
single one, it was just raining, like, the entire time. Like, you could not make it up. So I challenge your good weather.
You ran away from the UK weather, from the rain from the UK, and just jump into the rain of Canary
Yeah,
Islands?
basically, I just
Gosh.
pulled the clouds with me. They just followed the cruise ship, and they were like, "No, Jen, you will not have sunshine."
Well, the nice thing about building telescopes above a mountain is that usually the clouds are below.
That's true.
At least some of the clouds, not only,
Yeah.
not all of them, but some of the clouds are below, so you can see them and enjoy the clouds without being worried of losing all the nights of observations. I'm sorry, I didn't finish the answer. Yeah, I remember right now. Yeah. So these instruments, so ARPS North and Geno B, are located mounted at the Telescopio Nazionale Galileo in La Palma, Canary Islands, while Espresso and ARPS, the twin of ARPS North, are both in Chile. One in La Silla, ARPS is in La Silla, and at the 3.6-meter telescope, while Espresso is in Paranal at the BLT.
So, of all these telescopes and instruments that you use, do you have like a favorite discovery or a favorite object that you've looked at with them?
Yes, I do. The first planet I started working with is was Kelt 9b. Kelt 9b is still my favorite planet because it is the hottest planet known.
How hot is hot?
Hot is 4,000 Kelvin, which means that it is hotter than several stars in in the universe.
Yeah, I was just thinking, like 4,000 Kelvin is like around about the temperature of sunspots on the surface of the sun, right? It's around that. That's astonishing that there's a planet as hot
Yes,
as those.
it's hotter than most of the atmosphere. So if the most of the stars are M-type stars, Kelt 9b is hotter than most of the stars.
And that's these red dwarf stars. So
Exactly.
why is it so hot?
So the way we compute temperature is related to the stellar parameters and the distance of the planet from the star. So we do
Mhm.
not actually know its temperature because we went there and we measured them. Of course, we compute what is called the equilibrium temperature, and we assume that the planet has this temperature because it is located at some distance from the star, and the star has its own temperature, and so an amount of light, certain amount of light arrives to the planet, and this irradiation causes that temperature. So the reason why it is so hot is because it's so close to its star. We are talking about an A-type star, so the star is pretty hot itself with 10,000 Kelvin temperature, and this planet is located at 1/10 of the distance of Mercury from the sun.
My goodness.
It's basically surfing on the sun.
Yeah.
And the star is a giant star. It has a
Yeah.
2 point something the radius of the sun. So huge star. The planet is huge because it's an ultra hot Jupiter is larger than Jupiter, both in radius and in mass.
And is it sort of puffed up because it's so close?
So the being puff depends on the mass of the planet, not only on the closeness to the star. Because if the planet is massive enough to stay, let's say, compact, to have a large surface gravity that can retain all the gases surrounding it, or the
Okay,
outer
yeah,
layer of gas. It's not puffy. So I won't say that Kelt 9b is a puffy planet because it has a
because it's massive.
yes, it's massive, like 2.8 Jupiter masses. So
Okay.
it's really massive, and it still has an extended atmospheres, mostly because the star is so close, and it's a hot star that keep irradiating the planet. But still, it's not what we usually call puffy from this point
Okay.
of view.
What at which point we can stop calling it a planetary system and start calling it a binary system?
It happens that objects like that with large temperatures and close to the star may be mischief for a binary system. But when you collect the spectra, you can clearly see that the two are not two stars. You will see two different spectra, while it's not the case.
And so looking to the future, what do you think telescopes like the ELT and things like that are going to impact, the studies of these ultra massive Jupiters and also, the small planets? What do you think?
So at this point, we are good analyzing the big one, and we are still not good enough analyzing the small ones. So I want more to focus on the ones that are large enough to be analyzed right now, that have a signal in order to corroborate our analysis, our pipelines, to be able, once we're going to have the next generation of instruments, to know what to do with the spectra of smaller planets. Because ELT, for example, will help us a lot with this huge size, 30 meters diameter.
So it's like, so sort of right now, you think it's all about study the big ones because the signals are stronger, they're easier to understand, hone the skills, refine the knowledge, and then when these big telescopes come online, that's then when we can get into the super Earths, the Earth-sized sort of worlds, things like that, based on the knowledge gained from learning how to analyze planets through studying the giant ones.
Unfortunately, the problem with smaller planets is that you are able to detect them around smaller stars. Otherwise, with the detection methods that we have, we are not able. So there is this selection effect. You have small planets, but only around small stars. And small stars are usually affected by stellar activity, which can pretty much mimic all the things that we are able to observe in an exoplanetary atmospheres. And you need to collect a lot of spectra, a lot of transits, a lot of light to be able to fully analyze them. Analyzing smaller planets, it's what you need to start thinking about finding biotracers, for example, or trying to see if there is life anywhere else, or at least signs of that. But right now, I'm working on refining the analysis that we have, trying to see if we can develop some other ones. So when ELT will be ready and observing, we will need to collect, let's say, one spectrum instead of collecting 10, and
Okay, yeah.
so we will be able to fully focus on smaller planets.
And when ELT will be ready, available, ELT or all these huge facilities that, as you said, will collect more light, do you really have an idea what are the answers that they can give us? I mean, to which questions they can answer for us about, I don't know, planetary formation, or you mentioned habitability, for example, right?
We do not know what we will see, but we can start thinking what to expect. That's for sure. At least from my experience, for example, the single line analysis in the atmospheres of ultra hot Jupiters. If during the time that we build these instruments, we for example identify a line or a feature in a spectrum that can be linked with habitability, with the presence of life, what we call a biosignature. At this point, we can try to look for it. Of course, I'm not going to look for a biosignature on Kelt 9b, a planet which is
Yeah.
hotter than stars. But we can start thinking about doing that on planets that are more similar to the Earth. So we can try to do this. For example, if we will be able to distinguish among all the noise a feature, an individual feature that will tell us, yes, here we have something that reminds us of what we see on Earth. We can try to think about life. We can try to think about everything that we want.
With with the ELT. Yeah, so it's like the big questions around habitability for ground-based observations. You need that big telescope.
Yeah, I think so. So I think that talking about habitability, talking about biomarkers right now, with the resolution that we have right now, it's not feasible. At least from my point of view, right now, you can try to fit some molecules in the atmosphere, also low resolution spectrum, saying yes, this is a biomarker. We can see these, but I feel that we do not have the instruments able to do this right now, but
Yeah,
that we are gonna have them.
yeah, they're coming. Yeah. So I think before we finish, we're gonna ask you our signature question. It's
Oh,
always an interesting one.
Okay.
And it is, if you could choose a celestial body, so it's a planet, a star, something like that, that represents you, what is it and why?
So before starting my diet a few weeks ago, I would have said a black a black hole.
I know how you feel because I've been on like 2 back-to-back trips. One of them was a cruise and, 5 courses available.
Yeah, I understand.
Buffets, it's just it's not good.
I'm a black hole for sure during conferences and coffee
Yeah.
breaks and stuff like that. Honestly. But no, that's a tough one. Honestly, I study planets, but I do like the stars because
Yeah.
it's what we really have to investigate planets. You can't study the planet without having a star. And so I would say yes, a star, not a specific one, a bright, hot one, yes,
Yeah.
a red one, maybe yes, just because I like the color, but only because
Yeah.
I'm on a diet right now. That's
Yeah.
it.
Mattia, thank you. Thank you for joining us. Thank you for being here. Thank you for bringing us closer to the art and precision of spectroscopy and telling us how we can investigate the huge giant, mostly, with the amazing telescopes that we built here on Earth.
And thanks to all of you for listening. Join us next time as we look further into the cosmos and meet the people transforming starlight into discovery.